Hi, I am Ayan Kumar Bhunia from the SketchX Lab, University of Surrey, and I shall be presenting our paper, Iterative Text Recognition by Distilling from Errors. Text recognition is a long-standing problem in computer vision where a text image is converted into digital text content. Its applications include optical character recognition, navigation, and guiding board recognition, among others. However, a salient problem still hinders practical deployment. Prior state-of-arts mostly struggle with recognizing unseen or rarely seen character sequences. The absence of such sequences during training makes this task challenging. Our solution for this unseen problem is intuitive. We leverage an iterative framework with a feedback mechanism to give the model a chance to revisit its false predictions. However, simply knowing how feedback works is not enough. We still need to devise what information should be fed back to give a model its best shot at rectifying itself. For this, we resort to distilling knowledge from textual error distributions collected from state-of-the-art text recognition models. This is akin to humans who use prior experiences to help them to make corrections. For example, hello might be wrongly predicted as Nello or Bello due to partial structural similarity of H with N, or B. By distilling such error distributions into the feedback module, the model will gain knowledge of correct character associations. Unlike previous attempts of devising mostly deterministic feedback modules, we propose a cross-modal variational feedback network instilling benefits of variational autoencoder, a powerful class of probabilistic models. The prior knowledge from the resultant discrete character space is modeled using feedback network by predicting affine transformation parameters. Such parameters modulate the output activation map of TA via a designed feedback conditioning layer. The primary objective of the feedback conditioning layer is to propagate prior knowledge from previous forward pass prediction to the network T. This action couples the rich visual information extracted by TA, with the prior feedback signal coming from earlier prediction. In lieu of transforming each channel globally, we allow transformations that attune each spatial position of the activation map, formulated as shown in the slide. Our goal is to model a conditional distribution P of rho given Y, from a discrete predicted character space Y to the transformation parameter space rho of feedback conditioning layer via a feedback network based on conditional variational autoencoder. The variational lower bound of this conditional distribution can be written as shown in the slide. Ideally speaking, rho is supposed to adjust the activation map psi in a way that predicts the ground truth Y hat when passed through TB. Thus minimizing the cross-entropy loss between output of the next iteration Y dash and Y hat is equivalent to maximizing the likelihood of rho. We aim to decode the ground truth character sequence Y hat from Z by using an auxiliary character sequence decoder. This helps the module in learning an associative relation between candidate correct words and closely related erroneous instances. Additionally, using text-only data G alleviates the issue of limited availability of image-paired datasets during training. Hence, we adapt our feedback network to generate two components. One encapsulates relationship between Y and Y hat, while the other generates rho and injects Y into T for the next prediction. Algorithm 1 presents the joint training. We generate the text-only data G by collecting the top 10 beam search decoded hypotheses from different state-of-the-art models, to harness the error information from closest possible erroneous alternatives. G may consist of correctly or incorrectly predicted words, but does not contain any information from the testing set. This requires the feedback module to learn a language prior for fixing a wrongly predicted word, as well as for one-to-one character sequence mapping for correctly predicted words. The corresponding learning objectives in our proposed algorithm are shown aside. We incorporate our iterative design on top of three popular state-of-the-art feed-forward text recognition. Ours is a meta framework that could be added to any state-of-the-art frameworks. Highest values are marked in red. Improvement due to our iterative pipeline is quite evident in the disjoint train test split, over three state-of-the-art baselines. Performance in handwriting dataset in disjoint setup is much superior to its scene text recognition counterpart. This signifies that hand text recognition poses a greater challenge due to its free-flow nature of writing. We observe the optimal word recognition accuracy at t equals 2. We also compare with state-of-the-art in the standard or conventional setup, where red signifies the highest score. Our method performs best in this scenario as well. We present some qualitative results where our iterative framework outperforms the existing single feed forward pass mechanism. Finally, we present thorough ablative study to justify the contribution of every design choice on both handwritten and scene text datasets. Thank you for your attention.